Assalamualaikum warahmatullahi wabarakatuh. To my respected panels, my name is Aini Binti Ijaman with metric number AN190124. My beloved supervisor, Dr. Muhammad Kabel Abdul Aziz, and also my co-supervisor, Technologist Dr. Halim Hisham bin A. Razak. Regards for today's presentation, I would like to present my proposal of Bachelor Degree Project where the title is Flourine-Free Superhydrophobic Silicone Rubber Surface for Self-Cleaning and Anti-Fouling Properties via Deposition of Steric Acid Modified Kaolin Nanoparticles. Throughout my study, a guide outline has been created in order to complete this project. The presentation includes introduction, literature review, methodology, and expected result. Okay, for the first part of my introduction is research background. Superhydrophobic surface have been developed due to inspiration from nature phenomena. Water leaf and some other plants are known to have unique surface structure. When water drops off the white leaf surface, it will simply roll off on the surface instead of penetrating into the surface. While rolling off, water will transporting away any dirt or dust on the surfaces. Hence, roll-off of water resulted in self-cleaning of dirt and dust as well as anti-fouling properties of contamination and bacteria. To achieve roll-off and water repellency of the superhydrophobic surface, it needs to have rolling angle less than 10 degrees and contact angle larger than 150 degrees. High contact angle indicates that contact area between water droplets and solid surface is relatively small, which resulted to low surface wettability, making liquid droplets do not spread very much onto the surface. Moreover, high contact angle value lead to the air attrapment between gaps of the road surface, and hence water droplets do not hit all the surface areas. There is remedial application of superhydrophobic surface as self-cleaning, anti-fouling, and anti-corrosion properties. However, the recent development of modified superhydrophobic surface with surface roughness, Flourine-based by using fluorine-based nanoparticles are harmful to the environment. Moreover, the use of metal oxide also expensive. Hence, as alternative, Kaolin and low surface energy materials such as fatty acids that are environmentally friendly will be used. Improvement of recent development by using cheaper, safe and eco-friendly materials such as Steric acid and Kaolin with a lot of benefit also can be used. Next, previous development of fluorine-based superhydrophobic surface are expensive and harmful to environment. And surface roughness via pure metal oxide nanoparticle is expensive. So with more cheaper, safe and environmental friendly, using deposition of Steric acid modified Kaolin nanoparticles and Flourine-Free superhydrophobic silicone rubber surface will be developed. In order to overcome this problem, several objectives have been created. The objectives are to fabricate superhydrophobic silicone rubber film via surface deposition using Kaolin nanoparticles. Next, to characterize surface wettability and physical-chemical properties of the superhydrophobic silicone rubber film. And the last one is to evaluate self-cleaning and anti-fouling properties of the superhydrophobic silicone rubber film. Okay, to achieve the objective, there are few scopes of work have been identified as follow. First one is the silicone rubber film will be prepared and then Steric acid modified Kaolin nanoparticles will be coated on the surface film. Next, the contact angle will be used to characterize surface wettability and the physical-chemical properties will be characterized using AFM, SEM, and FTRR. The last one is the self-cleaning properties will be evaluated by dropping water on sample surface using polymeric powder, and anti-fouling properties will be evaluated by immersion of sample in organic contaminants. Okay, next let's move to the literature review. Surface wettability is one of the most important parameters affecting superhydrophobic surface. The provided picture is two states related to the surface wettability. The first picture is Casey-Baxter state that indicates that the rough surface is heterogeneous in nature because air pockets exist between the roughest of the gaps. The next picture is when the state that indicates that liquid entirely penetrates and wets the gaps between rough surface. Superlative rough surface is homogeneous surface with no air pockets between the gaps. To create superhydrophobic surface, fabrication technique with surface and low surface energy material is necessary. Chemical etching is one of the techniques that can easily roughen the surface. For instance, many organic polymer and glass surface can be etched and roughened using plasma technique. Next, in electrochemical deposition of metal film, surface roughness can be generated by electroplating under potential or diffusion limited conditions. Other than that, nanosphere lithography can be applied as a template to build topographically textured patterns on substrate materials. Moreover, solid method is another frequent utilized method that can induce surface roughness using secondary components. Lastly, nanoparticles deposition such as Flourine-based nanoparticles can create surface roughness. Okay, next fabrication technique by using low surface energy materials such as fatty acid together with surface roughness can create superhydrophobic surface. Fatty acid is known to be insoluble in water as their change length rises and can form a molecular film on the air-water interface. Examples of distinct fatty acids are steric, oleic, and allylic. Okay, now I proceed to the application of superhydrophobic surface. Superhydrophobic surface can exhibit self-cleaning and anti-fouling properties. The figure shown indicates the self-cleaning process of fluorinated polysiloxane titanium dioxide superhydrophobic coating. After sprinkling a spare layer of contaminant powder on the surface, a water droplet was placed on the contaminated surface. The contaminating particles were immediately absorbed on the water droplet surface when they came into contact with it. Then the pollutants were entirely absorbed by the water droplet after numerous cleansing process. Next, application of superhydrophobic surface with anti-fouling properties can be applied in seawater. Anti-fouling coating is used to inhibit the formation of biofilm in both biocide and non-biocide environments. Microorganisms cling to the surface of an object, known as substratum, and producing biofilm. The object is then develops complicated structure made out of group of microorganisms that multiply and coat the surface with biofilm. The common types of anti-fouling coatings are self-polishing coatings and fluorine-based coatings. Moreover, such spray can be utilized to create fouling self-cleaning coatings. The addition with zinc oxide nanospheres on the surface show good mechanical and anti-corrosive properties under aqueous subpop conditions. For the next part, I will briefly explain about my research methodology. The current figure shows the overview of experimental and method development of my research. In stage 1, which is the fabrication of superhydrophobic silicone rubber film, the surface deposition using steric acid modified Kaolin nanoparticles. There are 3 methods involved. Firstly, preparation of silicone rubber film, then will be followed by preparation of steric acid modified Kaolin nanoparticles, and lastly, coating of steric acid Kaolin nanoparticles onto silicone rubber surface. In stage 2, which is characterization of surface wettability and physical-chemical properties of superhydrophobic silicone rubber film, there are 3 methods involved. The first one is surface wettability via contact angle. Next is surface morphology and surface roughness via AFM, FTRR, and SEM. The last one is horizontal and solid bounce behaviors via high-speed camera. For the last stage, which is stage 3, involves the evaluation of self-cleaning and anti-fouling properties of superhydrophobic silicone rubber film. There are two methods involved. First, self-cleaning of the sample will be evaluated via polymeric powder. The next one, anti-fouling properties will be evaluated via immersion in organic contaminants.
For the last part of my presentation today is expected result of my research. It is expected modified silicone film to have superhydrophobic surface with a contact angle greater than 150 degree and a rolling angle less than 10 degree. Next, it is expected the deposition of steric acid modified Kaolin nanoparticles on the surface of the silicone rubber will successfully increase surface roughness as well as decrease low surface energy. Moreover, chemical bonding and surface morphology are expected will be successfully elucidated using AFM, SEM, and FTIR. Lastly, the superhydrophobic silicone rubber film with steric acid modified Kaolin nanoparticles is expected to have improved self-cleaning and anti-fouling properties. The figure shows the expected self-cleaning SEM image of sample A and sample B.
Okay, that's all from me. Thank you.